Professor Ravi Srinivasan to speak on the integration in finite terms with special functions, error functions, logarithmic integrals, and polylogarithmic integrals.
Thank you, William. It's wonderful to be back to, I should say, second home, because this is one of the places where I lived a longer time, and some of my good friends are over here, and many of them are actually here. So it's wonderful to be here. So the topic is essentially the PhD thesis of Yashpreet. So she's working with me, and she's going to graduate. And then I just figured out, one of you is actually doing the evaluation for the thesis as well. So that's it's good that I'm here. So initially this paper by a mathematician called Varadharaj.
Can you wait on the other board?
This board? Okay, sure.
Yeah.
So this mathematician, I don't think he is in academia now, but around, I think 1996 is his thesis, I think MIT, and then 2006, after 10 years, the paper was published. So this is in Journal of, I think it is in Journal of Symbolic Computation. So this paper was brought to me by my PhD student. So the paper is essentially doing integration in finite terms with dilogarithmic integrals. So then we did more research, and then we figured out that a paper by Michael Singer, Cabinas, and Saunders. So there they declared this problem of integration in finite terms with dilogarithmic and in general polylogarithmic integrals as an open problem, and they said that. And then in 1996 and 2000, where the thesis is, so there the author actually gave an expression for integrand, not the integrand but the integral. So what he was able to show is there is you can talk about so there is something called dilogarithmic elementary extension. I will explain what this is. So the question is essentially, if I'm given an element here, and then the question is whether the integral of this element is here. So these are differential fields. So whether I can integrate in this field extension. So what Varadharaj was he accomplished is that this he gave an expression. For the integral alpha. So therefore you cannot, if an alpha is given, you cannot test it whether you can integrate in such field extension, whatever the definition is. But he was able to show an expression for all elements of the integral. He was able to give some expression. So which I will show. So then the question is,
Can you just differentiate an integral and get the form of alpha?
yeah, but it will be of no use. It will have
because you have a known integral function.
Yeah, see, so this will have some dilogarithms. You when you take a derivative, you will get some expression. But the point is that there are too many variables. I mean, there's no you can't actually test anything with that. So the point is, then we thought there should be some way of actually finding an expression for alpha, which should be reasonable, that you can actually test. So that is when we got interested in this topic. So I'm just going to put some notations and terminologies before I move on to the state results. So the field that we work with is always going to be characteristic 0, and differential field essentially means it's a field with only one derivation. So it satisfies it's additive and satisfies the Leibniz rule. So the constants will be denoted by the CF. So here, it doesn't play much of a role, except that the extensions that we consider are all, it doesn't extend the constants. So in particular, the role of constants is therefore very minimal. And the last statement is essentially what it means to have a differential field extension. So you have two differential fields, one as a field, one is a field extension of the other, and then you restrict the derivation of the extension field to the base field, and it agrees. So as I was saying, so the problem is simply this. I can state it somewhat in a broader perspective. You take any differential field extension of base field f, then you can ask the question, if I take an element in f, can I integrate in this extension field? So knowing E, so is it possible to integrate? So that's the question. So the fields of interest are what are called, it was the fields that were of interest at some point is called the elementary field extensions. So I will come to that. So what we will be working in this talk is the field E is going to be a tower. Okay, so gotten by adjoining n number of elements, theta 1 up to theta n, all are in E, and it will satisfy certain conditions. So I'm combining the first three for obvious reasons. So theta I is algebraic, or it is an exponential, or it is a logarithm. When these three things happen, such a field extension is called the elementary field extension. So similarly, the other definition of what's called a Liouvillean extension doesn't pop up in this talk, but there is an obvious difference, which is that there won't be any u prime. Similarly, the theta prime is u prime over u is not going to be there. It's just theta prime belongs to fi minus 1. When such thing happen, you call this a Liouvillean extension. Here, these two definitions actually guarantee that theta I is actually an exponential of some element. Similarly, theta I is actually a logarithm of some element. So first of this definition that some of you might have not seen is what's called a logarithmic integral. So these are these definitions don't belong to me. So this is actually it goes back to, I think, a mathematician named Cherry, Cherry. Maybe I'll mention it later. So this is already known in the 85, 86. So they defined what's called a logarithmic integral. And then you can define what's called an error function. So in the usual case, it's the field of complex numbers with one variable. This u is x. So then you actually have the usual error function. So and then the third is what's called dilogarithmic integral. So this goes to at least the place where I have seen is Varadharaj's paper in Thesis 1996. So this is what's called a dilogarithmic integral. So log 1 minus u prime over u. So this dilogarithmic integral is, it's a special function, so is logarithmic integral and error functions. But this one is, though it is a special function, it actually satisfies when you define it, for example, over field of complex numbers with one variable and with the usual derivation, these are actually solutions of linear homogeneous differential equations over Ct, over Cx. So, in fact, these dilogarithmic integrals and polylogarithmic integrals, they come up when you do solve the inverse problem for unipotent algebraic groups. So these iterated integrals actually come, pop up there. But so therefore it is, though it is special, but they actually satisfy linear homogeneous differential equation. Okay, so that I need to point that out. And then finally, trilogarithmic integral is something that you have a dilog times logarithm. So you can actually see that it's going to be a iterated integral. So L2 is already an integral, and then you are further integrating this. So it is.
Is it the case that I don't see a pattern between logarithmic, dilogarithmic, and trilogarithmic?
The pattern is, maybe I'll write one example where the pattern will be.
No, I'm trying to form a second one, and I
See,
don't
if you
know
have
how.
ln of 1 minus x over x, so this is dilogarithmic.
Okay.
So you just divide this by x and take the integral. This will be trilogarithmic. This is an example.
But in logarithmic, you didn't have 1 minus u.
So
Right.
the word logarithmic integral and dilogarithmic integral, there is no connection.
Right. Yeah.
Because it doesn't say one.
From dilog, trilog, polylog, there is a connection.
Ah.
But why are we writing it? Simply because I'm following others.
Okay.
There's-
Okay.
This is in literature, logarithmic integral actually means this. See
Okay.
this for example, this
So
function.
the pattern should start from the dilogarithmic.
Dilogarithm.
I
Yes,
see.
exactly.
I see. That's why
Exactly.
I'm confused. Okay. Okay. Good.
Exactly.
Thank you.
So you should think of before dilogarithm is actually logarithm. That's how you should think, because this is ln of 1 minus x is actually the integral of 1 over.
Yeah. Yeah.
So you should think of it that way: logarithm and then dilogarithm.
Okay.
So this is see, for example, this is the. This is also, Rosenlight proves that this is not elementary. One of this Mathematics Association of America paper. So he proves that. So that is an example of a logarithmic integral. Okay. So elementary functions. So I mentioned it before. That is simply that you have the first three hypotheses, or the conditions that I have stated. Algebraic, exponential, and logarithmic. So if the theta is one of these, then the extension is called an elementary extension. So some history. It's not complete, but
Yeah.
I just want to say.
And you said that this was extensions when you want to consider if it's one of the following is satisfied. That includes the dilogarithm, the trilogarithmic.
The previous one doesn't. This is elementary functions essentially.
It's not clear from what you said before.
Yeah. So what I'm saying is, when this happens, that is, if theta is algebraic, exponential, or logarithmic, then this has a special name. This is called elementary extension.
Okay.
However, what we are going to work later, that will have all these conditions. So this problem goes back to Liouville, and then Ritt has written a book, small book on integration finite terms, where there's a lot of ideas there. And then Rosenlight's theorem of, from 1968. So that is actually the culmination of, the differential algebra is getting into this problem and then starting to do expand the work further to include special functions. So. So after Rosenlight, so it was Moses, I think, almost pretty much the same time, whereas in his thesis he has outlined some ideas on how to handle special functions, and first of the results were shown by Cherry for error functions and logarithmic integrals, and for logarithmic integrals he has also written an algorithm. So that is using the rich algorithm. He has implemented that in what's called Scratchpad. I didn't know what it is.
What's in the result of this work? So the result is a criterion whether your function has an integral in some extension of error functions and logarithmic.
That is correct. That's correct.
And the
So this criteria is
starting field is rational. What's starting field is elementary function.
it's any differential field. The base field is any differential field containing.
How is it encoded?
How what?
How is it
Encoded,
encoded in computer?
Yeah, see there you have to actually, maybe you, what you do is, I think there are a couple of parts to this. When he proved the result, I think the base field was assumed purely transcendental over complexes or computable field, whatever the C is.
What's the differential structure there?
DDX, the derivation, usual derivation.
So just
And then you
Rational functions, what he's saying.
yeah, rational function field, but it could have more variables
but what one derivation?
with one derivation.
And how does it act on the variables?
Why you're so puzzled? It's just, for example, I can start with the field C, variable x, log x, e to the x. This could be my base field.
Okay.
So the derivation, so it's not okay. So.
Yeah, this is what I'm saying.
Good, thank you.
So, so later, I think Bronstein, I think he did something when he included the algebraic case. Okay, so so there's a paper by Singer, Saunders, and Cavinus. So this is somewhat extension of the previous work. So the error function, logarithmic integrals, all these are part of this class called EL, elementary functions. So this is all a class of that. However, the polylogarithmic integrals were not included, and it was posed as a problem in the middle of the paper somewhere. And also some algorithm for error function. I think that was mentioned in that paper, but not everything together, but just the error function. Okay, so after 85, it is 2006, but 1996 is the thesis of Varadharaj, so where he talked about dilogarithmic integrals. So again, the problem is this is not in the spirit of Rosenleit's theorem, in the sense that he is not giving anything for alpha. That is, so I will mention what Rosenleit's theorem is. It is not about the integrand, but the integral itself. So he writes a compact form for that.
So basically, the statement is if integral exists, if it is of certain.
It is of this form. So that is what it is. And then the another condition that he had was, so this f is actually a Liouvillean extension over complexes or algebraically closed field constants. So this is CF, this is the constants. This is algebraically closed, and this is the Liouvillean. So he uses this result heavily in his work, and so the point is, once you have some relation, see the whole the thing is, you actually assume. So first you have to have a hunch on what the expression is going to be, and then once you produce the expression, then you descend at each, because this is E is actually f theta 1, theta 2 up to theta n. So each step you descend, keeping the expression alive, and then finally when you reach f, if it is over constants, such expression he uses Rosenleit and Singer result to actually show that show further that this expression comes to whatever the desired form that he wanted. So for that purpose, this Liouvillean assumption was very important for him. So he had it in his hypothesis. So I'll tell you with some main points from the thesis. So the thesis is about extending the theorem to error functions, logarithmic integrals, dilogarithmic and trilogarithmic integrals. So this means your extension field will have all of this arranged in some way, and then you want to produce an expression for alpha, which is in the spirit of Liouville. That is, it has to be if and only if. So given an expression in a of certain form, then you should be able to say whether it is there in the extension field or not. So these two assumptions, that f is Liouvillean over CF, and that the constants are algebraically closed. Both are actually not needed in this proof. So it works for any differential field, and the constants need not be algebraically closed. And then finally, so we give, in the sense, necessary and sufficient condition for an element alpha to have a integral in the this extension of our desire, which is built by error functions, logarithmic integrals, and dialogue. Okay, so we'll move on to Rosen-Leight's theorem. So Rosen-Leight's theorem is essentially that if I have an elementary field extension, so if I take an element u in E and whose derivative is in F, then the u has to be a linear combination of logarithms plus an element coming from the base field. So this is Rosen-Leight's theorem, or what's called Liouville's theorem. So here the constants Ci, the Ci are all constants, and the G and W are all coming from the base field F. Okay, so this is if and only if. Once I have an expression like this, it's obvious that I just adjoin log Gi's, then you get a logarithmic extension where u is there. Similarly, the other way is the one that you actually have to work, which is given an elementary extension and an element u whose derivative is in the base field, then you have to actually show. So he uses the proof is by so-called what's the first principles. You are looking at 1 theta. So if it is algebraic, then he shows how to. If I have an expression like this on the extension field, and it is gotten from the previous field by adjoining just one element, then he shows how to descend, where the theta is now either algebraic or logarithm or exponential. So each case you just descend. So that's what it is. So now we'll come to dilogarithmic integral. So dilogarithmic integral is given by this formula. So it also has a power series representation, through which you can actually, when you take the derivative term by term, you actually get this integrand, which is g prime over g times log 1 minus g. So as I said, for example, you encounter all of this in differential Galois theory. These functions appear. What we have to give a name for these things. So the name is DEL. D for dilogarithmic, E for error function, and L for logarithmic, arranged in ascending order of the alphabet, and then he gave del. So that's the thing. So so one thing that you observe over here is I'm not allowing algebraic elements in the extension. So that is the same case with Varadharaj's theorem as well. So he talks about only purely transcendental one. So the algebraic case, the algebraic case actually gives you a lot of complications. Already these will give you quite a lot of complications, especially the presence of exponentials. But the algebraic elements, I don't know how to do it. So at this point, okay. So what we have is exponential, logarithm, error function, logarithmic integral, and dilogarithmic integral. This, it appears in any order. So such an extension is called the DEL extension. And there is a DEL expression. So I will tell you what the expression is. So the expression is something like this. So this is the one that is of primary interest. So we are actually going to get an expression for the base element alpha in this particular form. Okay. So it somewhat resembles Liouville's. You can actually see that this AI, since the AI's and BK's are constants, the integral of each of the sum is actually the logarithmic integral, and in the error function type, this summation that is happening over here, that is also when I take the integral, it is just the error function. However, I cannot do the same for the first terms whose index set is this I. So here the Ri's are not constants. Okay. Instead, the Ri's itself is actually a linear combination of logarithms. Okay. So this is so as I said, first you have to first you have to look for a suitable candidate. So actually thinking about the suitable candidate, what is going to be the suitable candidate? That is essentially the maybe the time-consuming part of this work. So you actually have to find an expression. So there you have to actually come up with some examples and try to see what sort of expression that you are going to get, and then it's a leap of faith. And then you work, and then you see that it actually is the expression.
Just to clarify, so am I right that the first term is just any quadratic polynomial in logarithms?
Quadratic polynomial in logarithms. Yes, more or less.
Okay.
That is correct. So it's going to be so that is the non-linear term that comes in. So that created a lot of problem with in Varadharaj's work. That's why he actually stopped at the integral itself. So the point is, what we are going to show is to get the if and only if condition, the CIs that appear that will also have some more tighter conditions. So that when I show the result, I will explain. So you're right. So that's a non-linear. There's a quadratic term in logarithm actually comes in.
But any quadratic polynomial can be there.
Any is so. There is some more condition on CI. So I will explain what it is.
But as it's written.
As it's written, yeah. So now I will just tell you this one particular thing. When this linear combination is so when Ri is not a linear combination, when Ri prime is exactly say this expression right here, then each term is actually a dilogarithm when you integrate. So you can actually see that Ri is Ci log 1 minus Gi. That is what it is. Then each term is actually the derivative of a dilogarithm. Okay, so the previous one, it is not that these terms doesn't directly correspond to dilogarithm, whereas in this one it does. Okay. So when the aj and bk are 0, I call it d expression. That is just to make sure I don't have to repeat this statement again and again. So the d expression essentially means that this logarithmic integral and error function terms are not there. We are only looking at the dialogue, the terms that comes out of the dialogue, and the very last term. So some more definition. This is very standard. So what is called a logarithmic extension, and so that is you just attach logs from the ground field. It is not in any it is not iterated in a as a tower, but it's all the HIs are actually coming from F. And so we say something is transcendental dilogarithm when dilogarithmic elementary extension if theta I is exponential logarithm dilogarithm but not algebraic. So it satisfies one of these. So with this, I will tell you the first of the, so the whole point is this. So in Rosenleit's theorem, you take an expression that you think should be the expression for the alpha. Then what you do is at each step you when theta is algebraic or exponential or logarithm, you try to descend. So here what we are going to do is a similar statement. So it's similar but different from Rosenleit's approach. So if I have a transcendental dilogarithmic elementary extension, in fact it's dilogarithmic error function and logarithmic integral extension, and I assume that element's derivative is in the base field, and then the u prime admits a special del expression over logarithmic extension of f. So the special expression is simply the one that I have showed you here. So the special means so that summation, so the Ri is actually logarithm. It is not a linear combination of logarithm. So Ri is simply a logarithm, in which case each term, each term that corresponds to the index set I, when you integrate, you actually get a dilogarithmic integral. So the theorem says that if I have an element u in this extension whose derivative is in the base field, then then the derivative actually admits a special expression. But it is not over f at this point, it is over a logarithmic extension of f. Okay. So when it is simply the dilogarithmic extension, that is, you don't have error function and logarithmic integral, then u prime admits a d expression, because the a case, the constants, both the constants are 0, so you actually get the special, what is called the d expression. So this is the first step. And the second step is the induction procedure. So suppose I have f theta and then I attach log y1 through yn, and each yi is actually coming from f theta, then what we have is, the lemma tells you that you can actually descend to the lower one by simply attaching logarithms actually coming from f, not necessarily from f theta. So every time, so you have this field f theta 1, f theta 1, theta 2, and so on. So when I have the, you take any part of the tower, and if I attach some logarithms from the lower tower, and suppose I know that this v admits a special expression there, then I can simply attach logarithms from the base field f, and then I can get a similar expression. So finally, so what this will tell me is, finally I can descend all the way to an extension which is built only by logarithms, and I have a special expression over only an extension field built by logarithms, and then after that you can actually produce the main result, which I will show a little later. So what you would get. So an example, I just want to quote an example here. So if I have to write a non-trivial example, it's already somewhat complicated. So you bear with me as I go through the example. So you have suppose I attach, my ground field has these 3 elements, z, log z, and then this product. Okay. So I can, I can take this extension field E, where the E is actually f attached, I am attaching log z and then 2 dilogarithms to it. And I am taking this particular expression V. So you can immediately see that this V is actually a DEL expression that is easy to compute. In fact, DEL expression with the error term and the logarithmic integral term being 0. So you have this. So what you can actually show is the integral of V is actually in E. So that is easy to see. If I choose my U to be this sum of these 2 dilogarithms with a V0, the V0 is actually essentially what it is over here, what I have written in the next line. Then you can actually see that this U is, the derivative of U is in fact V. So the V is chosen in such a way that the integral is actually in V, in E. So the point is this. So if I have a del expression like this, when I simply attach logarithm, only in this case it is just only one logarithm, then you can actually write this U prime as a special expression. So initially it may not be special, but after I do the logarithmic extension, then it becomes special.
Do you want, on the third line, do you want the prime to be dtz or ddx?
It is Z. It's nice.
So,
Is Z.
on the third line, you have the prime is ddx.
Oh, where is? Yes. There is no X actually.
Yeah, okay, so the x should be.
The X is Z.
Okay.
So that's the first of the typo I need to correct.
Yeah.
So what I'm saying is that, so the point is U prime has an expression like this. That is, U prime is V in this case. It has an expression like this. But this expression need not be, just a sum of dilogarithms. It is a sum of dilogarithms only when I extend it to, when I throw in this log z. But otherwise it need not be. Okay. So this also you can check that one can actually check that this U prime cannot be written as a D expression over F, whereas it is over F log Z. So this is actually the main result. So the main result is if I have a transcendental del extension, And if I have an element u in the extension field whose derivative is in the base field, then all this holds if and only if u prime has this expression, and each of these, so the Ri and SL, see initially the del expression I showed, the first two terms are combined. So this is where I was saying that there are some conditions over the constants. In fact, you should be able to write this u prime into two of this summation, where there is this additional conditions that come in. So the Ci's, A's, D's, all these things are constants, and B's are all constants. So each of the patch actually looks like the Liouville type, what it is. And the converse is also true. So whenever I can write u prime in this form, then it belongs to some del extension. So you can actually find one where the integral is actually there. Okay.
Is such an expression unique?
Which, the u prime?
Yeah, u prime.
Yeah, the uniqueness, I don't know. I don't think it is. So the point is then, the hope is when suppose you want to write an algorithm, you at least have to say that there is only finitely many cases that you have to check. But I think that is possible, depending on the base field that we are taking. I mean, it's a finite transcendence degree field, that this should be possible.
So the point is that if I give you V, u prime rather, in some form, in some field called F.
Yes.
So let's say we take some concrete F with some generators.
Yes.
And I write it.
So then the first step would be to write like
Write it
this.
in that form, right?
Yes.
So is there a way to do that?
Yeah, so that is what we are working on right now.
Okay.
So you once a function is given, you have to actually find a way to write all of this. So this is the initial first step into the algorithm.
Right.
So how do you write it? And then so you also have to say that there are only finitely many ways to write it.
Why?
I mean,
if I got one way, would it be okay?
Yeah, but that one way may not satisfy this condition. So therefore, you cannot rule out that the integral is not there. I mean.
Oh, so you're saying that for the same element.
There may be multiple ways.
You can write in two ways, and one of them looks like that, but it doesn't satisfy all the conditions.
Yes,
The other one does.
that is possible.
Okay, it's possible. Thank you.
Okay, yeah. Okay, so this is another example. This is an example to explain this particular situation. So this is so for example, what I can do is, so if I take F as this particular field, so you can actually see this 5 appears twice. I mean, you can put anything you want instead of 5. 5 is just something that I threw there. So the whole point is this. So this expression as such is a del expression, and you can actually check it is of desired type. So for that, what you have to do is, you have to choose. See, there is in this case all the A, J, B, K are all 0, and you have exactly 2 terms. The index at I is 1. The index at L is 1. There are only 2 terms. And here actually you can check this condition over here. Okay, so that is.
So you have actually some matrices here, right? Like CIP.
Yes.
And maybe DIL.
Mm-hmm.
That
need not be square. It could be anything.
no DIL.
Yeah, they are not. They need not be square matrices.
So what you're doing really is that.
Oh, they are in this
Right,
case, huh?
Right.
Yeah.
So the CIP that appears in the R's of I prime as the first term coefficient, and
No, AIP doesn't appear. This DIL.
Right,
This
DIL,
appears.
this one.
This is the condition.
so
This
that
is the only condition. See, this
Right.
comes from this second term, and
right.
RI comes from the
right,
first
this is
of the
This
summation.
is the dialogue case, I guess. Okay. So that actually when you actually substitute into your u prime expressions in the first two terms, right?
You can't substitute anything. Here is prime and there is just
Oh,
Ri.
I mean after integration.
After I take the
Yeah, after you take the integral.
integral, yeah.
When you write the Ri in
Right.
logs,
You can substitute all.
then the other as logs.
Yes, and then there is
Then that's a become a
yes, that is correct. That is
That's
correct.
fine.
That is correct.
Now, okay.
Absolutely. That is the point. And you will actually see that in here. See, this has become a product.
Right, become product.
So this has become a product where the entries are now expressible in terms of the field itself. Okay. So then what you can do is you just so you can rearrange and then you can write you know how to integrate now. So the integral is simply that it is minus L2 of x. So that is the point. So this you can combine. This you can do only in this extension field. As such, you cannot do. So you have to go to this extension where you get this special expression. Okay. So I will quickly mention the Varadharaj's result. So he uses what's called a Bloch-Wigner-Spence function. So that is this dg is given by this. Okay. So the derivative is actually this thing, and this 1/2 plays a very important role. So this is such a thing is called a Bloch-Wigner-Spence function. So then what the theorem that he proves is that if an element u belongs to this transcendental dilogarithmic elementary extension with the u prime is in f, then u can be written in this form. So this is the expression for u itself. Okay. And you can actually see that there are many variables here. See h, f, g and all that. When you take derivative, so you don't get something, you don't get an expression for u prime in f, because there is going to be logarithms also. See, this fi is not a constant. So logarithms and all these things appear. So this is no longer an expression inside f. So you have to go to a field outside f to have an expression. Okay. So this also we actually prove using our results, we can actually derive this statement. But now Varadharaj needed these two hypotheses, that it's Liouvillean and algebraically closed field are constants. Those two you don't need anymore. So you can derive. So it simplifies the work. And also Varadharaj's result uses some. In fact, it's quite nice in the sense that he has actually found a new identity involving dilogarithm, and he uses that to show that you can write the integrand in this particular form. So I think this is the example that I showed earlier. This particular v, what you can do is for this particular v, you can actually write it in terms of the Bloch-Wigner-Spence function. I thought I will show you how that can be done. This is exactly this particular function. So what you have to do is, this is just a calculation. So you have to actually take the derivative and then you have to combine certain terms and then integrate it back to get this. So this will be the corresponding Bloch-Wigner-Spence function. Okay, so I will quickly go through the trilogarithmic slide because the results are quite similar. However, the calculation complications, so that actually exponentiates from dilogarithm. So the trilogarithmic elementary extension. So I'm just introducing this one more condition that theta could be a trilogarithmic integral. So trilogarithmic integral essentially means theta is derivative is g prime over g. Now you have L2 of g in the integral. Okay, so similar expression you can write. So now you have two terms. The first term is simply the dialog terms. Okay, the second term is the ones that comes from the trilog. Because trilogarithm is actually something of this kind and then you take the derivative. So you have these two terms. And then similarly you define what is special. So special is the one that each term in the summation, actually when you integrate, you actually get dialogue or trilog. As such, when you integrate, you don't get anything, but special if it is of this particular form. Okay. So then similar definition. So instead of logarithmic extension, we actually want, what we need is, this is for the induction step that I was showing for the dialogue. There is a similar thing that we have to do for trilog as well. Here, this definition is that I'm going to call the extension E as a dilogarithmic extension if it is generated by logs and dialogues. But however, all the y's and z's, they are actually coming from f. So it is not actually a tower. It is, you are actually adjoining everything. Everything at, in some sense, it's one level. It is not a multiple level. So the analogous statement is this. So if I have a expression in a differential field which is of the form f theta, and then you attach logs and dialogues coming from f theta, then the expression actually descends to an expression where now all the logs and dialogues are actually coming from f. So each stage you descend like this, and then finally what you have is you will get a special expression over an extension which is gotten by adjoining logs and dialogues, and then from there you descend as a one-step. There is a one-step descent to the base field, and that's where you get the big expression. Okay. So in the process, for doing this process, she needs a special identity. So I will mention this. So this is something that she has found. So the special identity is that if I have f, so what I'm doing is f is an element in capital F theta. However, I can write f as a product like this. This is actually going to the algebraic closure. If I go to the algebraic closure, the numerator polynomial and denominator polynomial I can split, and I can write it as a product where my ai's and the ai's and similarly the bj, which is 1 minus f, they are integers, not necessarily positive, because the denominator powers I'm putting it in the numerator. So then L2 of f can be actually written in this form. So the thing is, right hand side has L2 of eta. Eta is actually coming from the base field. And then you have these expressions. That is, the very second term has L2 of a simple function like this, theta minus alpha j over theta minus alpha k. Okay, so the nicety is, it is reduced to something that looks, though it looks quite long and somewhat complicated, but it is simple. Each term is easy to understand. So that's the point. And then you have a quadratic expression that involves logarithm. Okay. So this is actually used in the calculation of that lemma that I showed earlier. So Varadharaj proved a similar identity, but for the Bloch-Wigner-Spence function. So this is actually a combination of couple of derivative of couple of dilogarithms. So he proved a similar thing. So this is the result for trilog. So it is quite similar in nature. You can actually see that this RIL appears here as well as here. Similarly, at the next level, you can also see this constants appear. There are some conditions in it, but once it satisfies, then you can actually, once you find an element that satisfies all this, then you can go back. Okay. So the point here is the expressions of this kind, especially these are somewhat Liouville type. This can be checked because each of these portions are already implemented in axiom. So suppose I give a function in a proper field, then I can actually check this, whether my function can be written in this way. So this is where I have a hope that maybe since the patches can all be solved, so maybe this expression can also be done. Maybe it's hope, but hopefully we get something. So there's one more term, and there's some more condition here.
Symmetry.
Yeah, some symmetry is there. Yeah. So these are references. You know, I was telling Phyllis that I thought I will put a picture of from 2007. That was first time I came here to give a talk where almost all people were here, barring few. So
maybe we should take a picture now.
we can take a picture now, and maybe I come back here 10 years later, and then we can share it. So thank you for your attention. So this actually is not 2018; it's actually 19. Though everything was done in January of 2018, the paper is actually published only in 19. So.
Any questions?
Yes.
I heard from people in other area that many identities with d-logs and polylogs, they are somehow classified in terms of some Hopf algebra structure. So is it similar to what you see? All these conditions can they be explained in terms of this multiplication things?
Maybe, but I don't know about this.
Okay, maybe we can talk about it.
Yes, certainly. So Hopf algebra structure, as in where does it come? The dialogue? Is there a? Do you know any?
Well, they call this motivic integration because they all integrals of some rational functions iterate several times, and then there are some geometric reasons why there is a Hopf algebra structure, and it seems that they can recover the very huge identities from very simple reasons looking at the geometry.
I would be very interested in that.
I can point references later.
Talk to you about that. Yeah.
Could you go back to any one of the complicated slides?
Any one of them?
Yeah. Okay. Let's take this one. It doesn't matter. So I noticed that you are trying to identify elements down in the base field F, so that it has an integral in some complicated tower expansion.
Yes.
Correct. Now, in those towers, you allow the logarithmic integral, which is the integral of 1 over log.
Yes.
Okay? And you allow error function, the integral error function. Okay. Now, I see that in all this complicated expression, it looks like that the log integral and also the error are kind of independent of the logarithmic part of it.
Yes. So throwing in these two is of moderate value.
Is what?
It's of moderate value in the sense,
Right.
in the sense that
basically,
yeah. So they are
very independent. Is that correct?
Yeah, it is very independent. This is just to show that you can combine them.
Right.
There's nothing more to
But
it.
that makes it more complicated. So
Yeah, the calculation is therefore it's complicated. So see, there is some calculation
what I'm saying is
complications.
that it doesn't affect the logarithmic part of this thing. When you try to,
It doesn't affect.
right, it doesn't affect it, right?
Yeah.
So can you somehow separate them and then use this kind of independence as a separate result, so that you don't have to always tack on this log integral and the
See,
error?
that is the thing. I thought about it. See, for example, this is the same thing, right? I don't think there is much of, there is not even going to be interaction between trilog and dilog.
Okay.
See, because this is somewhat a higher transcendence in some sense.
Right.
But when you are putting together, you see, for example, I can't just prove dialogues and then you extend it to, include
right. No, you can show some
that is
independence.
not
Maybe-
possible. So what happens is, even though it is a log, you actually, when you do the calculation, you have to take everything together. I know how to say this, but the point is, I tried.
So let
And-
another way. If I put it another way and say, so suppose there is some relation between, let's say, GI and UJ. Would
Yes.
that affect your result at all? It doesn't seem so, because the condition down below, the two colored lines, has nothing to do with UJ, and the other one has nothing to do with the VKs.
Yes, it doesn't, because see the but nonetheless, when you do all the calculations, so what happens is you have to show that it doesn't depend. So that's the point. When you have to set up, when
But
you set
what
up the
I'm asking-
calculation,
Yeah, I understand. So what I'm asking is, can you separate that as a different theorem? So that you don't have, so that when you iterate, I mean, let's say instead of a trilogarithm, you do a quadrilateral and so on. So you don't have to keep repeating doing this kind of saying that this is independent.
yeah, I mean, that you can do, but the only, see, as I said, these two terms, one can write theorems without these two.
Of course, you can set up to zero, for
Yeah,
example.
so you can write a
But
theorem.
what you're saying is that even if you allow the TEL extension to include these two kind of generators,
But the main theorem, you have to take all the expression together at once and do this.
No, I understand.
I couldn't
No.
find a way to split these two and connect it. That's what I can. This is what I think you are asking. But-
right. I'm asking that, can you first of all separate these two so that you don't have to keep doing that? You know, you're saying that, I'm saying that if I have a TL, or whatever you like to call it, extension, and then I'd have the result so that those two terms doesn't appear, and I have a result when those two terms appear.
I will
can
combine
combine
them here.
them.
No,
There's no way.
no way. I tried. Let's say that I tried and failed.
Okay, all right.
But maybe there is, but whenever I looked into the calculation, I felt that you have to take all of them together.
Okay. Well, I mean, the way you state
See-
it, of course.
see, because this
No, the
result-
way you stated, yes.
A priori,
But
this
I'm
doesn't
asking-
say that
I'm
they are
asking
all
the way
like.
you attack the problem, to solve the problem, maybe you don't need to.
See, I'm not assuming any algebraic independence. I think the problem
I
comes
understand.
from that.
Right.
So I'm not assuming any algebraic independence here. So
Well, but
that
you are,
could be
but
dependence.
you are assuming the independence in the tower.
In the tower, yes.
Right. I mean,
Because I'm not allowing algebraic things.
That's right. I mean, each tower has a new.
Yeah, so
Transcendental.
however, logarithmic integral could be present in a dialogue tower. You see what I'm saying? That is where I'm saying that I'm not assuming algebraic independence. See, for example, so maybe I'll just try. See, I'm not saying that my towers are proper in this
No,
sense.
no,
So, see, I can attach theta 1
Yeah,
and theta 1, theta 2.
right.
But I'm not saying that, see, theta 2 is defined as, see, the u and log u comes from here. Let's say I have only j there is only one thing. So u and log u comes from here, and then you have an integral here. But this I'm not assuming to be transcendental. This theta 2
You're
could
not?
be here. No, this could be here.
I thought when you define transcendental, that's what you said.
No. See, this tower can be transcendental by being transcendent degree 1 extension, like this. I'm not saying I'm attached, see, I'm not attaching a theta I which is algebraic. That I'm not doing. However,
But you're saying that theta 2 could be algebraic over F1.
no, theta 2 cannot be algebraic over.
Right, so it's transcendental.
But theta 2 could be inside. Theta 2 could be here in F theta 1.
If it is there, then of course it's algebraic over it. What are you saying?
Yeah.
No, if it is, no, that is allowed. That's what, it
What
cannot
is
be
allowed?
purely algebraic. This is not purely algebraic. The theta 2 could be here in this field.
Algebraic
How
of
can
degree
it-
zero.
Yeah.
Rational, but not.
Rational. it's
Right,
called.
so it's not transcendental.
No, so therefore what I'm saying is,
But he said, I thought you said that each one is transcendental over the previous one. In the
Purely
definition.
transcendental.
Can you show the definition of transcendental?
no, I'm not saying it is transcendental, so I'll show you.
T is transcendental. T-E-L.
No, what is a transcendental extension?
I'll show you. This is what it is.
Okay, it's called transcendental if this, and
Transcendental.
each theta I is transcendental over
Oh,
the previous one, you said that.
That's true from
Yeah.
this.
No, but
That's
one
what you
second, one
said.
second.
That's what is
Yes.
written up
Well,
there.
we don't know what's algebraically dependent these days.
No, see,
You better not say that.
I think you want to say the extension is not trivial.
the extension is
Yeah.
non-trivial.
Yeah.
Yeah, so that's what I wanted to say.
Well, that's not the word transcendental.
That's not what it is, yeah. So, see, the theta is not proper algebraic. That's what, see, when I, see, what could happen is,
You're
if I-
just saying
if I
that,
write a-
you're just saying the two fields are different,
Yeah.
Yes.
yeah.
yeah, different.
just different.
That's different.
Yeah.
then you shouldn't use that word transcendental.
Yeah,
No,
transcendental.
so
No, absolutely not.
probably this is not written properly. But see, what I mean to say is that when you see, once you resolve the tower, so there I think there you are actually assuming that each theta is actually transcendental over the previous one. See, there are two problems. One is if I take u and log u, suppose u and log u both are in something like side f theta 1. So the integral could be there. So in that case, I'm not saying that the integral is always outside. That I'm not saying. That I'm not saying here. But if I resolve the tower into theta 1, theta 2, here in this particular context, I actually mean that they are transcendental.
How could that be? I'm not following. Well, okay. Now, let's another question. Okay.
Red proved that the incomplete elliptic integral of first kind, what Manin uses for the Manin morphism, is not elementary over C T and X, let's say. It's a,
Right.
He calls the parameter K, C of K and X. I have a question about the incomplete gamma function. As a function of the upper limit X of integration, it satisfies a linear homogeneous differential equation over the ground field of order 2. And the Galois group is solvable. And so the incomplete gamma function as a function of X, which is the Galois theoretic variable, is Liouvillean. Is it elementary over C of Tx? Do you know?
No.
I know there are dialogues and all those things in the intermediate differential fields when I was calculating them. And I was wondering if someone knows whether this Liouvillean would be an example of a Liouvillean function over the rational function field that is not elementary. Do you suspect it would be elementary?
No, if a dialogue is there, then it can't be.
Dialogue is there,
Then it cannot
trialogue
be.
is there, everything is there.
Then it
but
cannot be.
I never thought of it as towers.
So in the this is a parameterized situation, parameterized differential fields, right?
Yes, it's a parametric differential Galois. All the there are very important special functions that
But in one variable, this incomplete gamma function
integrals.
doesn't satisfy the
Incomplete
differential equation,
integrals.
right? That's
Could you
some
do
differential
things with
transcendence is there.
Incomplete integrals as functions of the upper limit of integration, and let T do whatever it wants, the parameter, or the parameters.
So what is this? This is integral 0 to x.
Yeah. X to the T minus 1, e to the minus 6.
T minus 1 e to the
I'm being sloppy.
e to the minus t, yeah?
X.
Yeah, e to the minus.
But I shouldn't be using the same variable as the upper limit, but do that indefinite integral, throw out the x from the upper limit, and it'll look more proper to a Calculus 1 student. And I remember Michael just commented, it's Liouvillean. And I said, huh? And because the Galois group
Is solvable.
is solvable.
Yeah, so if you have dialogue, trilogues,
Yeah,
so I was saying that so that
Yeah.
that actually
elementary.
comes from the unipotent part of the.
Which makes the incomplete, if that's true, it would make the incomplete gamma function very different from the incomplete elliptic function of first kind. If anyone's got hold of that book or can get hold of that book by writ, it's a very nice proof that this elliptic integral is not elementary. Have you moved it all into the list of incomplete integrals as special
No,
functions?
not. There was one problem that was mentioned to me. What if you include hyperelliptic integrals in this?
Yeah,
You
you
can-
can do that too, yeah. Yes, because there's been so much work, so much computation done on them.
Yeah. That would be interesting.
Yeah, It's just as functions of x, which is let the parameter do its thing.
So the calculations are very,
Yeah, I think,
it scares the
Yeah.
moment you start to do, I mean,
yeah,
it's quite
probably
scary.
not, probably the same techniques.
Probably similar, one can do it. I don't know, so it was mentioned that Badora used K-theory, I don't know how you use K-theory here, but.
I was wondering if the Galois theory could help, but the Galois theory doesn't help much for elementary over elementarity, does it?
There is a way of
What are the
doing that.
Galois groups of
So
elementary
there's something,
extension?
but I think you change the definition of what is called elementary to, so that the Galois group is actually abelian. So the Galois group is abelian, you say the functions that are in the field extension is
Or the
actually elementary. I think this is in
component
Andy's,
of the identity.
Andy's book, I think he has. But then the definition has to be changed. It's
Okay.
not this usual definition.
You really have to get your hands dirty.
So then he actually shows that integral e to the minus x square
Yeah.
doesn't belong to a Picard-Bessio extension whose Galois group is
that's interesting.
abelian,
Oh,
and therefore it
oh,
is not elementary. So he actually given a proof. like
right,
that.
yeah. There's been a lot done since Rid, as you,
Any further questions?
yeah.
Not, then we thank the speaker.